Hello everyone and welcome to the presentation of the design and simulation of a centrifugal pump. This will be the structure of the presentation.
Are widely used in various industries. For their creation, it is important to predict how they will perform before building them, which requires a deep understanding of the behavior of different flows under varying operating conditions. With this goal in mind, computational fluid dynamics technology was developed. Currently, research aims to greater accuracy and power in prediction. Numerical analysis of cavitation in submersible pumps and investigation into emerging technologies focused on designing pumps with lower energy requirements can all be found. In order to delve into the world of CFD simulation, an effort was made to design and simulate a pump that presents a proposal for geometry that meets the given specification and to determine the performance curve. Additionally, specific objectives were set such as building the pump's geometry and importing it into the CFD program, implementing physical models, meshing and boundary and initial conditions, running simulation at different flow rates, comparing and analyzing the obtaining results with the curves provided by the manufacturer to assess their appropriateness. The pump geometry was created by following a series of steps that allow us to determine the necessary parameters for its modeling. First, we obtain the values for angular velocity, flow rate, and the optimal head from the manufacturer's curve. Then, we calculate the internal and external diameters of the impeller, the width of the impeller at the inlet and outlet of the blades, and the attack angles. Finally, we determine the number of blades that would make up the impeller. In the calculation of the impeller design, we use velocity triangles to accurately model the impeller width at the inlet and outlet. The results can be seen in this section. All these parameters are found in the table on the right. After this initial step, we use AutoCAD Inventor to design a 3D model on the impeller and the volute. For the volute, we ensured that the side clearance was around 30% of the impeller's thickness, while the suction and discharge nozzles were designed to measure 80 and 65 millimeters respectively. Both parts were assembled in the same software before being transferred to STAR. Lastly, we determine the type of regime the fluid belongs to by calculating the Reynolds number for water and oil, concluding that in both cases the behavior of the fluids is turbulent.
With the geometry, the pump was imported to a CFD software where each part, region, and interface were established. After that, the mesh was constructed with four different automatic measures, with two additional settings, such as customized thickness threshold and distribution mode. The meshing was an iterative process where various parameters, such as base size, had to run a mesh with a number of cells between a million and a million and a half. If this was positive, it was necessary to have a diagnostic without negative cells. With this, it could be possible to run the fine and the coarse meshes. These are the values of those parameters, noting that those with asterisk are related to base. And for the construction of the fine and the coarse meshes, just the base size was variated. Once the mesh was correct, some reports and physics were specified, knowing that the pump is functional for liquids. The difference between water and oil is reported in the physics because of the difference in density and viscosity. The turbulence model was important because of the force that the impeller implies over the system. For this, the turbulence model used indicates that a number greater than 10,000 for the Reynolds number was considered turbulent. It was calculated using the equation. Now the results. The mesh independence between the fine, normal, and coarse meshes showed consistency in the number of cells, as we can see in the table. Also, there are similar efficiencies, which means that it is not important that parameter, and the head and efficiency errors were below 3%. This is why the time is the most important parameter in the decision of the mesh, and, because of this, we decided to use the normal one.
Now we present the head and efficiency versus flow rate graph. In the head versus flow rate, we can see that the manufacturer's head decreases as the flow rate increases, which is an expected behavior. Water curve seems to also follow this behavior up around 200, in which the head of the water does not decrease as fast. This deviation could be the result of simplifications made during the CFD. For the oil curve, we can see its behavior is pretty similar to the water's. This is unexpected, as the oil should have lower head due to its viscosity. As for the efficiency for all curves, BEP is consistent around 70%. However, each curve reaches it at different flow rates, being the oil the highest one. Also, a lower head at the BEP compared to the manufacturer's value could mean that the pump may not perform as expected in real applications. For the mechanical power graph, we can see that the overall behavior is pretty similar. However, we would expect that the oil will require a higher mechanical power due to its viscosity, but it doesn't happen. Geometry design and impeller slippage could explain these results. In this graph, we can do a direct comparison between both fluids. As you can see, both peak at similar efficiency, being the water slightly lower than the oil. Likewise, both polynomial regression fit well with an R squared values above zero point 0.9. This implicates that the data closely follows the predicted models. For the manufacturer head versus CFD head analysis, the results show a partial accuracy, with around half of the data points falling in the interval of error. Also, the MSE for the water head value is 0.115. A small MSE means that the CFD simulation is capturing the pump behavior with good accuracy. These two conclusions slightly disagree with each other. This figure provides a visual comparison of the velocity magnitudes. For both fluids, these magnitudes likely increase with higher flow rate, where the velocity is more evenly distributed, indicating a better impeller performance. We can note this because the color scheme is brighter for the higher flow rates. The same analysis applies for the PEP velocity magnitude figures.
The following animations helps understand the velocity distribution throughout the pump. Also ensure smooth fluid flow from inlet to outlet with minimal recirculation or abrupt changes, which is key to efficient pump design. We identify patterns like recirculation zones or dead spots, revealing inefficiencies, while velocity gradients highlight areas of high shear stress, potentially leading to cavitation or erosion. In this slide, we can compare water and oil streamlines, showing that oil's higher viscosity results in smoother, slower flow, while water exhibits more turbulence. Going back to the cavitation phenomenon, here we can observe that occurs more frequently at higher flow rates, independently of the fluid, especially near the best efficient point, where the highest levels of cavitation are observed. As fluid velocity increases, pressure drops in the impeller above the corresponding vapor pressure shown as the maximum value in the scale of each fluid, leading to vapor bubble formation. These bubbles reduce pump efficiency and can damage the impeller over time. As for the Y plus observed in the impeller simulating oil, it has a lower value. As the flow rate increases, the fluid velocity and its gradient in the region near the walls also rises, as well as the shear stress at the wall, and therefore the friction velocity. The boundary layer region becomes thinner near the walls. The flow in this zone experiences higher velocities, but at the same time, the viscous layer decreases. It is also noted that the oil simulation have a lower YY plus because kinematic viscosity is a factor in calculating this parameter, and since oil has a higher viscosity, the YY plus value will be lower than the water. In conclusion, optimizing impeller and volute geometries is essential for improving pump performance and mitigating cavitation risks. To reduce cavitation and improve efficiency, we can increase the number of blades for better flow distribution, reduce impeller diameter to lower tip speed or and pressure drops, enlarge the inlet or reduce RMP to decrease fluid velocity and the entrance, smooth the transition between impeller and volute, and minimize clearances. As we continue to design pumps, it is crucial to consider the differences in fluid viscosity, as this directly impacts flow behavior and efficiency. For instance, oil's higher viscosity results in smoother flow patterns compared to water, which can exhibit less turbulence and recirculation of the flow. Looking ahead, in order to improve this kind of projects and results, research should focus on cavitation suppression, advanced materials, and multi-phase flow simulation, since these kind of variables also affect the results. Ultimately, this project has successfully met the specifications set by Grafans and demonstrated the efficacy of the simulation models used. By comparing our results with those of the manufacturer, we have identified both similarities and differences which can guide further improvement in pump design and performance optimization.
References. Thank you.